Hello. Okay. Hello, everyone. Let's get started now. So first of all, I would like to thank you all for coming today to Declaration Week for Mechanical and Space Engineering at York University. And I would also like to thank you, the professors and the staff and whoever who made this event possible today. We're gonna go up a presentation and we're gonna talk about different aspects of mechanical engineering, different areas of research, applications, etc. So let's get started. Yeah.
Okay, welcome to Declaration Week. So I'll first go over a quick introduction of myself. I'm Krishnika and I'm the first engineering representative at LES. And some of my interests are robotics, electronics, telecommunications, and some of my favorite courses I've done over the course of my second year is geophysics and space science, electronics, space communications, and many more. So I'll now pass it over to Kareem.
All right. Hello, everyone. So my name is Kareem. I'm your mechanical engineering representative on behalf of Lasso Engineering Society. I would like to thank you all for coming once again. So I'm a fourth year mechanical engineering student. My interests are aerospace, biomedical, and the rail industries. My favorite courses will be fluid dynamics, mechanics of materials, solid mechanics. They are different courses, by the way. Heat transfer and thermodynamics. The reason why these are my favorite courses is because they relate a lot to the areas of interest that I have. And today we're gonna go quite a bit into those areas. So I would like to welcome all the professors. We're gonna get started with Professor Thomas Cooper from the Faculty of Mechanical Engineering at York University. Please, round of applause to him. Thank you.
Oh, okay, great. So hi, everybody. I'm Professor Tom Cooper. I'm an assistant professor in mechanical engineering. Just a little bit about my journey, how I got here. I'm originally from Toronto, did my bachelor at U of T. Then I moved to Switzerland for a few years and in Boston for a couple of years and finally made my way back to Toronto, joined Lassonde in 2018, mechanical engineering. And here I run the Cooper Lab, which is a research lab, and we specialize in renewable energy, specifically solar energy. The courses I'm teaching this semester, you can see here, so it's third and fourth year courses, so I probably won't see you for a few years, but if you hang tight, then hopefully you can join one of these courses, heat transfer. And then the last two are technical elective courses. So in your fourth year, you have the option to kind of specialize and choose the courses that you're interested in. And so the two courses I teach are transport phenomena and energy conversion and storage. So these courses are quite useful for anyone who wants to go into the energy industry or even things like fluid flow, biomedical engineering. Transport phenomena deals with basically any types of flow, any types of transport processes. So I think some really interesting courses for you if you can wait until your fourth year until you get those nice electives to choose from. I'm going to skip through these course descriptions here and we can go back if anybody has questions of those. I want to tell you a little bit about some of my research that I'm doing. So I'm predominantly interested in solar energy. Now, it's probably not the type of solar energy that you might think about when you think about solar. Probably a lot of people would automatically think about solar panels. I do a little bit of work with solar panels, but the majority of what I do is actually trying to convert sunlight into other useful things. So what kind of things? Well, predominantly heat and fuels. So why heat? Well, I had this number on one of my previous slides, but does anyone know in the residential sector, what fraction of all of the energy we use for anything is just for heat? Just heating your room and hot water. Any idea? Any guesses? Yeah, that's pretty good. It's more. 82%. So 82% of all of the energy we use is heat. Okay, that's the residential sector. It's a bit lower in commercial and industrial. Nevertheless, heat is a very important form of energy. So to put things simply, what I like to do is heat stuff up with the sun. Okay, take sunlight, focus it much like a magnifying glass burning a leaf, but at a much larger scale. All right. And when we do that, there's a whole range of different temperatures that we can go. We can go all the way from 100 degrees Celsius, room temperature roughly, all the way up to 2000 degrees Celsius, right? So it depends on the type of technology and the process that you're using. And that huge temperature range allows us to do a lot of different things. So we can even do things like industrial process heat. So power industrial processes using renewable energy rather than burning fuels. We can do desalination. So there's actually ways of taking seawater, heating it up with sunlight and converting it into fresh, clean drinking water. And then when we go up to the really high temperatures, we can actually start to do some really interesting things. We're working on a pathway to produce fuels. And I'm not talking about hydrogen, I'm talking about gasoline, like liquid fuels, the same fuels you use to run your automobile right now, using two ingredients, just two ingredients. Anybody know what those two ingredients are? Any guesses? Yeah. Even more basic than that. I'll give you a hint. One of the ingredients is sunlight. Yeah. Yeah, very good. Even simpler than water. What's more abundant than water around us? Air. There you go. So we're working on a process to produce liquid hydrocarbon fuels from two ingredients, sunlight and air. I know it seems a little bit like magic, right? And there's a lot of technology that goes into it. The gist of it is to make a fuel, to make a hydrocarbon fuel, you need hydrogen and you need carbon, right? Air around us has moisture in it. That's a source of water, which can be converted into hydrogen. And the air around us has CO2. That's a source of carbon. It can be converted into carbon. Okay? Then we take that hydrogen and carbon, mix it together in some advanced processes, and we can actually make liquid fuel. So we can make things like ethanol, but we can also make gasoline. We can also make jet fuel, right? And when we do this, of course, when we burn the fuel, we're emitting CO2 and H2O, right? So we are emitting CO2, but guess what? The exact same amount of CO2 that we extracted from the atmosphere to start the process. So it's entirely CO2 neutral. There's no net CO2 emissions. Even better, because the process starts with extraction of CO2 from the atmosphere, you can actually decide, hey, look, I'm going to actually sequester some of that CO2. I'm not going to use all of it to make fuel. I'm going to put some of it into the ground, sequester it. Then you're actually CO2 negative. So you're taking, let's say 100 units of CO2 from the atmosphere, you're using 50% to store and sequester in the ground, 50% fuel. So it's actually a closed carbon loop. It's completely CO2 neutral or even negative. And it also has the advantage of being compatible with existing industry, fueling infrastructure, existing. So that's kind of the goal. That's the dream. And of course, there's a lot of engineering and science that goes into making that. So when you really boil it down, what it comes down to is kind of these three main areas. So solar energy, understanding the flow of sunlight, how to best capture it. Thermal science, we're converting sunlight into heat, so we need to understand how to do that efficiently. That requires knowledge of heat transfer. And we also need new materials, right? We're talking about very high temperatures here, so we need new materials and new systems. A few of the pictures of some of the different things we've been looking at. If you're interested, send me a message. My email is was it at the bottom? My email is here. You can send me an email and I can show you the lab on the 5th floor of the Bergeron if you're interested in any of this research. Thanks so much, everybody.
All right. Thank you so much, Professor. So very good insights that we have. So now I'm going to bring you to another professor from the Faculty of Mechanical Engineering. His name is Reza Rizvi. Please, a round of applause to him. Welcome, Professor.
You'll just next slide. Okay. All right. Hi, everyone. Welcome. My name is Reza Rizvi. I'm an assistant professor here in mechanical engineering. And the title of my slides up there is the name of my lab or my research lab, which is handful polymers and inorganic composite structures and surfaces labs. But the acronym is PIXEL, so you can remember that easily. Next slide. So just a few things I'll talk about. I'll talk a little bit about my background. Then I'll talk about what courses I teach and also what research I do. Finally, I just want to spend a minute talking about why mechanical. Why should you choose mechanical? Next slide. So just a bit about me. I guess, yeah, Tom and I were in the same school, but different department at different times. I did my undergraduate and a little bit of my graduate school in material science and engineering. Right, so closely related to mechanical, not exactly, but close enough. And then my graduate school, like doctorate, was in mechanical engineering department, also at U of T. I spent a few years doing some postdoctorate research at University Health Network at Toronto Rehab Institute in downtown Toronto, and then another year or so in UCLA in Los Angeles. Really great time. West LA is beautiful. Santa Monica and everything. Yeah, amazing. But very unaffordable, right? Yeah, so then afterwards, since 2016, I've been an assistant professor. First, I taught a few years in a city near Detroit called Toledo, Ohio, at the University of Toledo. I was teaching mechanical engineering. And then after that, in 2019, I joined here in Lassonde. Again, like Tom, my Toronto is my hometown. I grew up here, so it was a little bit coming back home. Over the time since then, you know, I went through my work, we've done a few good things, like we have 4 patents to our name, 20 plus journals, more than $1 million in funding, and multiple industry contracts. Now, when I say we, who am I talking about? I'm not talking in just third person, but it's me and my research group. So the students that are, you know, really leading the research that we're doing. Next slide, please. My favorite quote that I love to say to people, and it's at the back of my business card, is by the inventor, or sorry, the discoverer of vitamin C, which is that discovery consists of seeing what everybody has seen and thinking what nobody has thought. So I love that quote because, you know, discoveries are all around us to be made, all right? It's just a matter of you thinking differently than how people have approached in the past, right? So a lot of my inspiration and, you know, what I teach my students also is, you know, if something's been done, don't discard it, right? Like, you know, look at it from a different angle, a different perspective. You know, there's more to be learned, more to be thought about it. Next slide, please. Okay, so just a quick note, why engineering for me, right? You know, I was into sci-fi a little bit, like Star Trek and, you know, some of these Marvel, DC comics. But the superheroes that really resonated with me were the ones that, you know, didn't use all that fancy supernatural crap, but like, you know, they had their resources, right? Like Batman, or whether it's Iron Man, Tony Stark, right? So, you know, that sort of really inspired me to pursue engineering, where, you know, what are the possibilities with new technology, with new advances that we can have, right? And if you look at some of the Star Trek from the 60s, you know, the tricorders and the communication devices they had, well, that's a reality, right? Like we have that stuff now, right? So oftentimes our imagination is our only limitation. And, you know, that's where, you know, engineering can really be something fulfilling, like a mission for us, right, to pursue. So it's really about how to make that reality. Now, what courses do I teach at Lassonde? So I teach the Eng 1101 course. I've taught that a couple of times. You guys have probably all taken it or will take it. Really just introduction to problem solving, communications, and ethics. I also teach
I
Eng
just joined it, so
2003,
in case there's like
one of my
further
regular courses. That's an effective
things right
engineering
now, but
communications course. I think most of you guys will take it next year. In that course, we do resumes, cover letters, interviews, co-ops. So really life essential skills, right? That other courses kind of don't really cover. We also do how to do technical report writing, right? So technical writing is very different than how you learn to write in high school, maybe, right, in English. And basically, this course, I think it's one of the most important courses that you'll ever take in your engineering degree. It's basically how to sell yourself to the world, right? You can know everything you know about if in the world, but if you cannot communicate that to others, then it's no good, right? And finally, the last course that I teach is Mech 3409, which is on machine elements design. This is an interesting course. You all will take it. It's compulsory, but it's all about why stuff breaks, right? What can we do about it? But then why does it still break, right? So even if we design it, it's still gonna break. And a big answer to that is fatigue or fatigue loading, right? So cyclical loading. And how do we plan for that, right? How do we maintain things? How do we design things? We learn about the most important design equation, which is the safety factor equation, right? So, in engineering, you always are working with safety factors. So we learn how to use those, right? And I'll pass around just one example. In this course, you will learn why things break. And so here's an example of how in an engineering setting, things can break. Try to put this part together. There's a lot of unintentional things in design that happen and things will break as a result of that, right? Okay, what research am I doing? My research is mainly in regards to composite materials and plastics or polymers. Polymers are great materials to work with because they are super light, right? They're one of the lightest material classes that we have, right? Density around 1 to 2 grams per cc. And as a result of that, they're amazing in transportation industry, like aerospace, automotives, etc. And so there's a lot of amazing things about them, but then there's a lot of disadvantages as well, right? They're inherently weak. So a few of the questions that through my research we're trying to answer is how can we make them stronger, right? Other things that we do explore in my research is also what else can we do with these composites or these plastics, right? What new applications can we seek? And so we try to make new surfaces, right? So here's an example of a composite surface that if you put under your shoes, right, is going to stop you from slipping and sliding in ice, right? So those are some possibilities that we can hook up in the lab and hopefully take it to the factory, right? If you can only do it in the lab, there's no good, right? You need to be able to mass produce stuff. So those are also some questions that we answer in our group. Other research that we do also is regards to nanotechnology, right? So materials at a very, very small atomic scale. We're talking about, atomic level. So here's an example of an atomic property manifesting in the macroscopic domain. Here's a highly ordered pyrolytic graphite, right? If you shine it with a laser, you can see that these layers of graphite, right, they conduct heat very fast along the plane, right, where it's glowing red hot, radiative heat transfer, 1,000 degrees or more, right? If you touch the sides, you will get burned. But if you touch the top, the heat transfer is so weak that it's almost at room temperature, right? So here's an example, like if we can capture that property and use it in our different processes to solve various problems, right? Some of the problems like Professor Cooper talked about solar energy and fuel capture, right? But other problems as well, right? So it doesn't have to be only that. Next slide. So one project in my group is on supersonic synthesis of these 2D materials. So you saw the big picture, right? But if we want to take that and we want to make some things like composites out of this, we need to be able to mass produce these nanomaterials. So one of the processes we've come up with is that we've taken these graphites and other materials that are called 2D layered materials, and we've shown that if you pass them through a supersonic nozzle, well, it's truly really hypersonic, But if you pass them through a supersonic nozzle, you can start to separate them into very, very tiny individual particles. And so I have here an example, a dispersion that we made, guess what, 5 years ago. And you can see that this is still in dispersion. The telltale sign is that if I take a laser, there's something called shadow. That indicates to us that these particles are super duper tiny, all right? And they were made 5 years ago and they still haven't settled, right? So they're really stable suspensions. So this stuff can be really useful. What can it be useful for? Next slide. Well, we can make advanced composites out of this, right? One of the problems that we were solving with a partner of ours at University of Toledo was bottling and food packaging, right? So food packaging spoils with plastics, right? Why is that? Because plastics, unlike glass and glass Tupperware that you use food with, right? Plastic can allow for oxygen diffusion, right? Oxygen gets into your container, it spoils the food, right? So the diffusion coefficients of plastics are 1,000 times more than glass and other ceramics. So as a result of that, we can add these tiny particles to try to stop this oxygen diffusion through it, right? So we tried to make these, and this was 30% improvement in the diffusion barrier, right? So I have here another plastic film that we took those particles that you see in solution and we made a barrier. So this could be your future Coke bottles, right? And allow you to have, 30% longer shelf life. Next slide. Okay, another project I'll talk about is on biodegradable electronics, right? So you've heard about biodegradable stuff like food packaging and really low value stuff. But what about electronics, right? So we have a huge electronic waste issue in around the world as well. So some of the electronic waste, like very few of it gets recycled. And for low value stuff like RFID tags, you can just forget it, right? None of that is getting recycled. It's just being thrown away and it's polluting, right? So what we're trying to do in our lab is that can we use these nanomaterials to make biodegradable electronics, right? So we have a process here, and I'll pass around the sample where we take a laser beam and we can convert graphene, right? Which has graphene oxide, I should say, which has lots of nice oxygen groups and it can dissolve in water, right? And we can make that electrically conductive, right? That's important for electronics to conduct electricity. Next slide, please. So using our process, we've been able to show that we can make RFID tags. So wherever the laser shines, and that's what you're seeing in the sample, right? That's where the laser shine, and it's very conductive, right? It's one of the most conductive carbons you can get. And as a result of that, we can make RFID tags. So you can see that as we bring the tag closer to the emitter, it's lighting up an LED, right? At the same time, next? We can take the same tag and we can dissolve it away back into water, right? And that's really good because this is made out of carbon, right? It's not harmful to the environment and it can be retrieved if we want to, right? So pretty useful, right? Application of nanotechnology. All right. In conclusion, I just want to say a few things about why you should choose mechanical engineering. If it moves, if it heats up or powers up, you can be sure there's got to be something mechanical about it, all right? And mechanical engineering, you can think of it like the one jack of all trades engineering, right? So if you're not sure, what to do mechanical, right? But even if you are sure, mechanicals are employed in every sector imaginable, right? There isn't a single sector they don't touch upon, right? And this can't be said for other disciplines, right? So I'm sorry, right? But, mechanicals have that advantage. And so, mechanical engineers, like I know mechanical engineers that design and operate all of these things, right? Wind turbines, aerospace, fine, that's great. But what about chip foundries for Intel? What are mechanical engineers doing there, right? So they're needed there as well. Robots and rovers for NASA, CSA, private companies, right? Software systems. What are mechanical doing with software? Design is a big part of mechanical engineering, right? So that design thinking, that design methodology is really important, right? in these applications. At the same time, if you do engineering, right, doesn't mean you need to do a traditional engineering route. You can branch out into other things. I know people who are CEOs and VPs of companies, right? They're investment bankers, lawyers, and doctors, right? So, it's that knack, that aptitude that you'll get through these 4 years, right, of engineering. All right. So lastly, thank you so much. If you want to talk your heart out about career advice, etc., I'm always available. There's my email and my office. All right. And you can reach me anytime. All right. So thank you, and choose mechanical.
Appreciate it.
All right. Thank you very much. Okay. So now. Okay, so the next person who's going to present will be Professor Jinjun Shen. He will be live streaming from Zoom. Let's see if he can hear. There he is. Hello, Professor Jinjun. How are you?
Oh, good. So actually, I'm
Oh.
not a professor in space engineering. Can you hear me?
Hello, Professor Jinjun. How are you?
So actually, I'm
Oh.
not a professor in space engineering. Can you hear me?
Yeah, we can hear you.
Yeah, it seems there's
Hello,
some
Professor Jinjun.
echo.
How are you?
Actually, I'm
Oh.
not a professor in space
Sorry.
engineering. Can you hear me?
Yeah, we can hear you.
Yeah, it seems there's
Hello,
some
Professor Jinjun.
echo. All right. So again, so can you hear me? Hello? All right. So okay. So as mentioned, so I'm not a professor in space engineer. Sorry, in mechanical engineering. I'm a professor in space engineer. Is that okay for me to present now? All right. Okay, great. So, okay, so I will share my screen with you. And before I share my screen, and I'm going to give you a little bit of introduction to myself. Again, so my name is Jin Yunshan. I'm a professor of space engineer, and I'm also the department chair of Earth and Space Science and Engineer. And in our department, we do have two engineer programs. One is the space engineer, which is the program I'm in. And I joined York University in 2006. And since then, I have been working as assistant professor and a third professor and a full professor. And since January 2018, I became the chair of the department. So until now, before I joined to York University, I got my PhD from Harbin Institute of Technology from China, and I finished. I did a 2.5 year postdoc fellow at University of Toronto Institute for Aerospace Study, so UTIAS. Okay, so I'm not going to give a long presentation, but I'm just use a video and to show my research. Let me see whether I can share my screen. Okay, hopefully I can share my screen. So just give me a second. I need to do something here. Okay, can you see my screen now? sorry, I need to. Uh-oh. Yes, okay, good. All right, so I'm going to use the video to give you some ideas of my research. And actually, my research lab is spacecraft dynamic control and navigation lab, so which I created when I joined York University in 2006. And at the beginning, so I work on some space engineering related projects such as orbit dynamics and satellite orbit dynamics, orbit dynamics, and also satellite attitude control system. And in the past few years, I have focused on autonomous systems. So actually, on this slide, on this picture, you can see some drones and some ground vehicles my team is working on. And actually, right now, my team is focused on the dynamic control navigation of autonomous systems. And the autonomous system could be from a spacecraft to drones and mobile robot and self-driving cars. So I'm going to show you the video, and at the same time, I can give you some description of those elements in my lab. And by the way, so this is my research lab, which is in P3 building in P3 427A. And if you're interested in our research, and feel free to drop by our lab, and my student will be pleased to give you a tour of our lab. Okay, so let's start. Okay, so I'm going to stop here. So now you can see actually this is the flying arena in my lab, and now you can see a drone is flying in my in this area. And actually on the wall you can see there's several cameras, because when we drive outside and we can use the GPS for navigation. However, for a system indoor, we cannot get access. We don't have access to the GPS signal. So this is why we need some ways to do the positioning for those drones and the ground vehicles inside of the building. So actually here we're using the same idea, same methodology as the GPS we use outside. So basically we have multiple cameras on the wall. Actually, in this particular setting, we have 16 cameras on the wall. And actually, the idea is very similar to the GPS. At any time, so if an object can be seen by 4 cameras, then we can determine the positioning of the vehicle. So actually, if you look at this vehicle, there are some grid dots mounted to the vehicle. Basically, we call this as a marker, and the markers are used are used by the cameras to determine the location of the object, such as the drone and the ground vehicle. And if the object can be seen by 4 vehicles, then we can determine the position and the pose, basically the position and also the altitude of the object. So this is a flying of one vehicle, and this is the workstation. And actually, you can see this is the drone we use in our lab, and we've got 6 of such drones, all from the local company Quanser. So we call this as a Q drone. And here, basically, this is a ground vehicle. So now you can see this is the mobile robot, and with different sensors. For example, we have the connected camera for positioning, and also I think this one doesn't have, but we also have the LiDAR on the mobile robot, so we can do navigation, and we can do advanced control system design for this platform. And also each vehicle is equipped with a computing board. So actually, we use the Raspberry Pi, or we use the Jetson as the onboard computer. And also, we can add different sensors and actuator to this vehicle. So here is the robot formation. Now you can see this is basically this is the undergraduate student research project 2 years ago. And here is basically a vehicle swarm, and we can have the cooperation of multiple drones and multiple ground vehicles to collect together to collaborate for some tasks. And here is research topic we are working on right now. This is the drone transportation. Now it's a single drone with payload cable system payload. And here is the drone deliverer. So basically, we started the delivery of goods by drones. And this is another research we are working on. Basically, that is self-driving car. I will stop here. So now, as you can see, this is another type of the autonomous system. So this is self-driving car. And in this particular application, we started the decision making by the self-driving car. And to do this research, basically, we combine the machine learning, deep reinforcement learning, and the game theory to successfully identify or to develop the driving policy for each vehicle. And actually, yeah, so basically this is the hardware we are using to test our policy. We also use the supercomputer to do the machine learning and to learn the policy. Because as we have more and more vehicles involved, so the time consumption for the learning will be very dramatic. So then we need some simulation to run the policy, and then we need hardware to validate the developed policy and to see whether it will be successful in real scenario. So on each self-driving car, and it has a camera and also it has LiDAR. So this is another ground vehicle we're using in our lab. So basically, let me go back a little bit. So now you can see this is another ground vehicle we use in our lab for control and navigation purpose. And we also have the camera, kinetic camera here, and we have the LiDAR system. So basically, we do the multi-sensor fusion for navigation and also some advanced control system research. All right, so I think that okay. So basically, this is the logo of my research lab. So this spacecraft dynamics control and navigation laboratory. So I'm going to stop the video, and at the end, I want to say, because it seems that everyone is trying to use this opportunity to attract students to our program, and I will do the same thing. So basically, again, so I'm a space engineer, and you know, York has the only space engineer program in Canada. So we only, this is the only space engineer in Canada. So if you are really interested in space engineer, come to our program. And also, from the video I show you, and this is my research area right now, and you can see actually if you come to the space engineer program, you don't need to work in space industry. You can work on many different areas, such as self-driving car and robotics and drones and aerospace engineer areas. And actually, I have to say, space engineer is a really multidisciplinary research area or multidisciplinary program. And you will learn mechanical, electrical, computing, and control system. So you will learn many things, and then you will be able to find applications in many areas. So I will stop here and just see if you have any questions.
Thank you very much, Professor.
Okay.
Do you guys have any questions you would like to ask Professor Jinjun? Okay, thank you very much. Thank you, Professor, for participating in the Declaration Week event for space engineering. Now,
Hey folks, yeah. So now we're going to be hearing from our first guest speaker, Mr. Pete. He's had a 37-year career in engineering, working in software and technology development. He is a consultant and a former BlackBerry VP.
I think I can control that here. Hopefully everybody can hear me okay in here and also hear me okay on the streaming. So this is about a 40-minute presentation, so buckle yourself in, but I'll try to keep it interesting and with lots of videos and hopefully your attention. The topic that that I chose to speak about is the next frontier in warehouse automation robotics. And the reason I chose this topic, 3 reasons really. One is it's super interesting, and I hope you'll find it when it's done. Secondly, it is a field of engineering that brings together electrical engineering, mechatronics engineering, industrial engineering, electrical engineering, software engineering into one bundle, and without all of these engineers, really impossible. Thirdly, and maybe most importantly, it's something I know something about, and it's a lot easier to give a presentation on a topic that I don't know what I'm talking about. So, so that's why, and we'll kind of move on from here. So the agenda, try to be about 35 or 40 minutes, and then leave about 5 minutes for questions. There might even be a prize at the end for those that pay attention. So try to keep track of little details in the presentation, and you could be a winner. I'll talk about the world of warehouse automation and why it matters as much as it does, why it matters so much more now than it did perhaps 5-10 years ago. The associated engineering disciplines that make it all happen, and some words of advice perhaps at the end from just an engineering perspective that I hope will be helpful to many of you to see. Just a graphic of the journey that I went through, not to belabor myself, but I wanted to spend a couple of minutes on this slide to give a sense as to who I am and where I've been and what I've done over the last, interestingly enough, 40 years. What's crazy is that 40 years ago, I remember, being in the same position that you're in. 40 years goes by actually much more quickly than you would think, surprisingly. And I remember I was enrolled in the civil engineering program when I went to school at I graduated in 1983. And I thought I'd like civil engineering because I thought it was cool to design buildings, bridges, and make sure they were stable, until I took a class in graphics and realized I had no aptitude for it. I couldn't see things in kind of 3 dimensions the way I needed to. I struggled with the class and realized if I can't do that very effectively, civil engineering probably isn't the greatest direction for me to go. And then in the next term, I had an opportunity to take computer programming. Computer programming back in those days was in Fortran, and did it on punch cards. We literally typed our programs on hundreds or thousands of cards. You'd input them into the computer that was almost the length of this room. And then when you in and the computer read it, you'd walk over to the other side of the computer and you'd wait for this piece of paper to come out. And when it did, you'd look and see if you got, the result the way you were supposed to. If not, you'd have to go back to the terminal, put out a bunch more computer cards, put it in. You got it right. Ridiculous, archaic, crazy how much computers have been 40 years. On the other hand, I got bitten by the bug. I seem to have some aptitude for programming, and I liked it. Came a lot easier for me to craft. Electrical engineering, software, everything happened because of that decision. Programming. And on I went. So Graduated in 1983, and I spent about 7 years in computer systems development at a company called GIAC, which was a Canadian success story. And then I moved to IBM. And for about 7 or 8 years, I did nothing but hardcore technical or operating system development, hardware development. And then at IBM, I had the opportunity to flip a switch, and they were probably the best company on the planet, helping train you to be a technical manager. And I took that fork in the road and committed to myself that I would maintain my technical proficiency through it all, but I went on in path, and that I moved around a lot from industries. So first couple of jobs were in computer systems development, right hand side. And then I moved to logistics at a company called Descartes Systems Group. Pure.com kind of morphed into financial systems development at BCE Emergent, your arm with then I had the opportunity to move to RIM or BlackBerry. By the way, anybody here or even have heard of a BlackBerry device? So we really did revolutionize mobile communications, right? Everybody who was anyone used these little devices. That this is untethered the world effectively from their computers and work remotely. And we were a global phenomenon success story. Incredible opportunity to be a part of that. I ran globally for the company, enterprise software development. Spent almost 10 years there, and then switched industries again to get into warehouse robotics and warehouse automation and robotics at Dematic. Dematic happens to be the largest warehouse automation world, automating warehouses for the likes of Amazon. So did a lot of switching around industry. Really two main things other than switching those around. One, I spent 7 or 8 years again in pure hardcore technical roles. And after that, switched into management, progressively more senior management at IBM, and then got my first executive role, and then progressively. And I'll talk a little bit about what it takes to achieve some of those opportunities or get access. 40 years engineering goes by in a flash, 24 years in executive level positions, and then still working pretty hard in consulting. But spending also a lot more time than I used to. Okay. So, slide. So what is this thing about warehouse automation? Why does it matter so much these days? And it's because we do things differently now most of the time, right? So you don't as often go into a mall, presumably, some of you might, but most of you probably don't go around into a mall looking, browsing the aisles and seeing what it is that they have to have on the shelf, buying it. You're more likely to buy with a sense of purpose. Go online, you click a button, you look for what it is you want. It's this notion of an infinite shelf, the tyranny of now. I expect that the product that I want, I can find it on the internet. I expect it will be delivered to my house the next day. I expect that it isn't going to cost me very much for a delivery fee. It should be free. And what is it that enables all this stuff to happen? What is it, this magic when you order something? Show up at your doorstep sometimes in a matter of hours, certainly in less than 24 hours. It's automating these warehouses to make machines move virtually instantly, like enter on button. And if you look at e-commerce as a percentage of global retail, less than 1% in 2000, kind of exponentially grown decade by decade, 30%, 30. With a global market share of a global market of about $25 billion today, growing over 60 decade. And what this means is that there are a massive number of jobs in warehouse automation for engineers and robotics. One of the biggest challenges that is facing these days is how on earth are we going to get access to the engineers to deliver these solutions that I'm going to show you in the next 20, 25 minutes or so. So great opportunities, whether it's electrical, mechanical, mechatronics, industrial software, etc. So if you look at the roots of warehouse automation, Dematic is the company that I was most recently at until I retired a few years ago. It goes back about 200 years, but the first advent of things like electric conveyors existed back in the early 1900s. The graph here of Dematic's first electrical conveyor. Like you can still recognize them as being conveyors. And then Dematic's first automated storage and retrieval machine in 1962. Now, again, if you think of a warehouse, you don't want to have all your products sitting on ground level or on static shelving units that are get access to. You need machines that can very rapidly retrieve these products. And the very first one of those, again, was designed by Dematic in 1992, and it started to revolutionize how warehouses work. You could store products virtually up to the ceiling, and you didn't have to have people to get access to them. So let's fast forward a little bit and look at how things work today. So if you look at a warehouse in general, there are all sorts of technologies that including conveyors and linear sorters. An example on the left-hand side is from Dematic. These conveyors and sorters can move generally around 3 meters per second, sort cases 18,000 cases per hour. And it's really quite amazing when you watch these in action. It feels a little bit like Disneyland, where packages are just moving faster than the eye can see and being sorted into different chutes through different off ramps by these little orange shoes, as they call them. So let's take a quick look at the video, how that works. In that, when products get inducted and managed through this controller that you see, they get shot off by the shoes as soon as they reach. They merge in perfect timing as all the boxes are coming around at the conveyor and everything is controller. As they approach the sorter, they get scanned automatically. The scanning item will carry a slot in a conveyor, which then allow everything to be timed off there, shot off at the right time. So that's one type of conveyor. There are a number of other kinds that have to be considered as well. This is next one is a circular sorter from a company called Mech. It has the advantage to manage all kinds of irregularly shaped objects, can sort things much more quickly, around 4 meters per. It moves around 4 meters per second. Can sort up to about 3,000 cases an hour. Take a look at this one. As an example. There are these little cells, effectively, which have a perpendicular conveyor segment and divert the product as it approaches. Again, the product gets scanned with a cell called the circular sorter because it moves around in a big loop. It occupies a fair amount of space. But then at the end, when it gets to its particular diversion, it's shot off. Again, it's a component of an automated warehouse, needs to be integrated. It's a critical area. And there's some even more imaginative, interesting ones. This one is Cellumation, intelligent convey sort platform. Doesn't necessarily sort as quickly as some of the other ones does, but it does all sorts of crazy rotational scrambling rotation capabilities. Usually they're set up as little platforms. This one. Imagine a pallet being depalletized and one layer of that pallet coming off, and then it afterward. Happening here is these little wheels. The wheels are controlled individually, and it allows packages then to be churned and singulated in single file. And again, software is controlling all of this, and you have the ability to manage a warehouse using these. So almost you have to think of them as Lego blocks. How can I use that sorter and this sorter and that sorter in order to achieve the engineering goal? Okay, so then that was one aspect, the whole sortation. Then you think about storage. We talked about the first automated storage and retrieval machine. Automated storage and retrieval technology basically is a multi-billion-dollar market. One company called AutoStore has become quite famous. And their claim to fame is really to have the maximum storage density possible in a warehouse. So this situation, the totes are actually touching. They go all the way up to about 6 meters in height. And you can take a fairly distributed set of products and crunch them all together in a very small space to get as many products into that warehouse as you possibly can and get virtually immediate access to. The way this works is there's robots that go on the top of the racking system effectively, and they move there. The tote that has the product in it that gets ordered happens to be on the top. That's good. Otherwise, it'll dig down and get them from lower down. Naturally, the heavily ordered products percolate to the top, and those products that don't get ordered very often descend at the bottom. And you can get pick rates of about 500 totes per hour per person. And again, it's all about, think the Amazon scenario. How do I order products and get them? Let's take a look at the video. So imagine a warehouse getting scrunched together, so all the totes are together. And I can get a whole bunch more into a warehouse where they get together. And I have these little robots that are going on top of the grid. And this is the real life depiction of it. Now, when there's a tote that a particular robot has been instructed to go pick up, it will descend its handle, pick up the tote, and then person and get instructions. We'll get instructions to pick it, and then automatically the tote will put back into the system, and these systems cost, you know, $10–20 million sometimes, somewhere in that nature. But it's unbelievable because for deployment of a system like this, you save huge numbers of people that you otherwise need in a warehouse. And the ROI usually turns out to be about 2 or 3 years. So, okay, everything we've looked at so far has been moving products around or storing products. This is an example. How do you actually pick? We saw a little bit of the picking in the AutoStore example, but another way to automate a warehouse very inexpensively is just lights, and smart software. Here on the left-hand side is a pick-to-light system by a company called Telegraded. You have a conveyor running down the middle, and effectively the employee will receive, or the worker will receive light-based instructions as to where the picking has to be placed. So a light will go on in front of a certain bin area and say, pick 3 of these. They'll pick 3 of those items, put it into the tote on a conveyor, push the tote down, further down, it'll see the next light go on. They'll pick 2 of those, put those in, and all they're doing is running up and down aisles all day long, picking as fast as they can. So it's very labor intensive, but it's way better than having a pre-printed pick sheet on a clipboard that they walk around with, because all the software is controlling their movements as efficiently as possible. Relatively low cost way to automate a warehouse. Change that, and I don't have a video of that. Compare that as an example with goods to person picking, where the people don't walk around at all, but rather the totes are brought to the individuals out of the storage and retrieval machine. Costs a lot more money, but you can double, triple, even quadruple per hour. So it's always in this case, you see what's happening with the screen there, exactly what has to be picked. super fast tote exchanger that will exchange out donor tote and order tote. The pick has been done from the donor tote. They did all the rapid fire ad hoc with instructions from the screen. They're virtually error free because it's so clear the instructions to how that works. So that's a little bit about picking. So let's look at an example of a complete end-to-end automation system. So this is actually in the grocery industry. If you can imagine a big grocery distribution center. And in a grocery distribution center, there might be 50 regional grocery stores ordering hundreds, thousands of products, certainly many, many, many pallets every day of products. Those products need to arrive at the grocery store not only on time, but they need to arrive in aisle-friendly order. So all the products that are supposed to be depalletized in the store in a particular aisle or close to each other on the pallet, et cetera. And you want to do all of this with virtually no human intervention at all. Getting orders in from all these grocery stores, and let's have almost a dark distribution center where everything is done in a completely automated way. So in this case, this is an example from Dematic. It's a system called automated mixed case palletization. All the attributes of the products need to be known by the system. For instance, a basic pot needs to know the length, the width, the height, the load capacity, the weight, to make sure that when it's palletized, it doesn't crush other products. So it knows all the attributes. The way the system works, it receives homogeneous pallets from suppliers, soft drink suppliers, big suppliers, et cetera. Those get stored for long-term storage. Ultimately, when they're needed to process orders, they get automatically pulled out of long-term storage. They get palletized, delayered, singulated, much like you saw in the earlier example. They get stored in a temporary buffer system, which is another answer, so that they can be perfectly sequenced according to a software algorithm that has pre-established what order the items have to be palletized so that they are ready to be easily depalletized. So the amount of effort that goes into building a system like this. Take a look at what's back. So end-to-end system, you see, in this case, one layer of the pallet has been palletized. Products get singulated, they get turned around. Now they go en route. The buffer system, they're moved to different models, up to different levels. All of this is in preparation that they get taken out in perfect sequence, and that shuttles can deliver them just at the right time. Shuttle system, much like an auto store system, has something like, let's say, 30 aisles, 20 levels. Shuttles, and all of these are moving in sequence with one another to deliver the product ultimately to a robotic palletizer, which you'll see in a second. This is the algorithm that the software figured out how the packages have to be onto the pallet. You'll see that the robot is palletizing, moves it down, readies it for the next layer, stretch wrap it automatically. That is complete. It'll automated pallet conveyor to the shipping location. So these systems tend to cost in the neighborhood of $100 million or sometimes more. But it allows a grocery distribution center. In fact, many of the ones that we here in Canada are like this and are automatically sending these pallets. So all part of the whole warehouse automation space. Switch gears a little bit to robots. So this whole revolution of the bots, everything that we saw earlier in this presentation so far, everything's been bolted down, which makes it fairly expensive. These $100 million investments have to be paid warehouse. In this case, it really is as a result of what Amazon did. They acquired a company called Kiva in 2012 for $75 million. And this is how your Amazon orders get processed. When you order calculators, you order a calculator off Amazon. that yellow shelving unit that has a calculator in it that you ordered will brought directly to a associate that is responsible for picking your product. And that happens sometimes seconds after you hit order in your product. So it's moving the shelving unit, these portable shelving units, directly to the associate. The picking. There are many, many companies that are in this space, but Evo is the one. Now, take a look how this works. Imagine you placed an order in Amazon. All of a sudden, a bot will be assigned to your order, and it will, if they start moving these shelving units around, they become these little robot highways. No people on these highways. Dispatched to process your order, and as they move around processing everyone's associate here who light will go up in the particular bin where your calculator is. It says pick out how get processed and eventually packaged. The beauty of these kinds of systems is that they're not bolted down to the floor. You can start small, you can grow as your business grows. And basically, it's swarm bots that just are controlled by or orchestrated by robotic picking. If you notice, everything we've talked about so far, people have been doing, right? They haven't been robots. Warehouse automation is tough. There's some time for robots to do the picking. Not like manufacturing, where it's a fairly repeatable process. Billions of different SKUs. All of them are, many of them are awkward. They're hard to pick. And unless you can pick enough of them in order to come close to the dexterity of a human finger or the human hand, eventually it's a losing proposition. So there's been a tremendous amount of research that but they're getting there, and we're starting to see more and more robotic picking applications. That's going to grow over the course of the next several years. How they actually do it. Here again, in this case, you're getting a mixed tag thought what has the ability to change the end effect. And the goal is, can you pick up translucent? Can you pick up water bottles? Can you pick up things that have all these crazy irregular shapes? You can. Not really possible. But I think by the end of the decade, we'll see a significant percentage of now, all of this is controlled by great software, right? If you think about warehouse management systems, been around for a long time. They control things like warehouse execution system management. So you get people largely off of the warehouse floor, but there's a big control center. The form, any kind of issues that how to correct it, dynamic rush order comes in, the software will be prioritized how it process it. So software is critical to this entire environment. Getting back maybe full circle, you look at warehouse automation as a whole. How does it all together? Mechanical engineers are trying mechatronics engineers are heavily involved in the robots and the robotic. Industrial engineers generally are working on the overall concept, trade-off analysis, mathematical modeling. How do I put all these Lego blocks together to maximize electrical engineers, are working on electrical design, power system design, sustainability thing, ensuring that power is distributed from the software engineering here, continuous optimizing. Perhaps no industry where the different specialties within some words of advice. So that's the end of the, let's say, technology things. I wrote a book in my spare time since I retired. It's the commercial part. The whole focus has been on a demographic not unlike the audience here today. It's how do you maximize your career in engineering? How do you achieve your full potential? And it really is focused on, I think, are critically important. I talked about the experiences that I went through in my career that some were embarrassing, some mistakes that I made for years, decisions that I'm proud of that helped me along the way. All of them were learning opportunities. All of them were things that I benefited from and tried not to make the same mistake twice. Boil these principles down to 10. Build and maintain technical proficiency throughout your career, even if you are companies. It is so much easier to perform well. It is only one of the 10 principles, or one of the developing strong communication skills is critical. As possibly can. Being true to your words, listening carefully before you speak, giving everything. Prioritize truth and integrity above all else, even when they fess up to it. Willing to explore new opportunities when that little voice inside your head or that feeling inside your head. Maintain your composure. Don't lose your cool. Don't lose your temper at work. Figure out a way to the problem. And, that way, go out of your way to help others. Again, lots and lots of stories in the book about. I do hope and that it's going to help a lot of people in their. So as a summary, warehouse automation is growing rapidly. Lots and lots of engineering opportunities. Moving around in your career is a good thing to do from time to time. One of the greatest skills I think we all learn and with that, we have the ability to move from industry to industry. Maximize your potential. Your prowess is one. Need to build up the rest of it. Well, you don't necessarily have to find out the way to practice and make sure. So, does anybody remember what year Dematic built the very first ASR? Good guess. 1922 was when the first conveyor was the first ASRS machine. Good listening. I would like to present you with your very own copy of Decoding Your STEM Career. Right? I will. Yeah. So thank you very much. Any questions that I can answer for anybody? I actually, yeah, it's a great question. I talk about that in the book quite a bit as well, in that in general, and I looked at this when we hired people, you don't want to move around too quickly. And in general, my average was about 6 years, for sometimes I say 10 years, 9 years. Interestingly enough, in my case, I didn't move around that quickly, but you were very observant. What actually happened is that a small company was acquired by a larger company, was how I ended up moving what looked like a bit more quickly. But I mean, sometimes you have to move, and you have to look at it from a longer career perspective. But yeah, you probably don't want to have a resume where you don't show any loyalty whatsoever. You don't want to have, for a number of years, I've been at 6 different companies in 8 years, and question, well, how long are they going to stay here? So you have to look at some kind of commitment, longevity, and then trust your gut. Get as much as you can out of it. When it's time to move, you'll know it and move and jump in. But yeah, 5, 6 years on average is probably a pretty good average in a long general. Not great to be known. Job. Well, it was, again, I was fortunate that I worked at IBM. And IBM back in those days, probably still today, they had a system for everything, right? So it was a conscious decision. You had to be recommended by your manager to move in, and they started putting you on management training courses. And they were also very good at making sure that you maintained your technical knowledge. They were very helpful in giving me the opportunity to attend courses. It's an interesting topic. One of the courses that I attended, again, I've done several podcasts, and this always comes up in the podcast as well. One of the courses that IBM put me on was this intensive communication. And I was a terrible, like ridiculously bad presenter when I first started. Nervous. There was this one episode that I speak about where I was called 6 or 7 people. I knew the topic well, and had all the slides presented, sweating profusely. I'm embarrassed. A friend of mine came to me with a paper napkin to wipe the sweat off my brow. I mean, it was ridiculous. And I thought to myself, I really got to figure out how to present in a way. And IBM sent me on the presentation where you would learn how to present effectively, how to look people in the eye, how to trust yourself with the right words at the right time, how to put these presentations. All these byproducts that it helped me in one-on-one communication. It helped me in communicating in my personal life. On team effectively. I could talk effectively to my teams. I could present in front of thousands of people in an audience. But you have to commit yourself to it and learn and realize that strong communication skills are also an important part of it. What the difference was for me was I did just as much technical reading, but there were so many broader topics that I had to have knowledge of technical reading at a higher level. I tried to contribute to the technical contributions, but I wasn't actually make technical contributions, but I wasn't, making unilateral decisions. Being a member of the team, I felt that. I think that's what a good leader needs to do. They need to realize you're not doing the work anymore, but you still need to be respected by the team to the point where you're talking about things that ask good questions, and ultimately the buck stops with you, and you have to be able to make decisions. That's what I try to do. It's a great transition, but it's also a transition that led to huge numbers of mistakes. And at the same time, so at the end of the day, I think you look back, you can have a fantastic career in engineering, and you can far exceed any expectations that you ever set for yourself. In my case, I would say that I'm pleasantly surprised with how my engineering career went. When I look back at it, I certainly feel like I exceeded the expectations I had in my career. And I think the reason for that was that I committed myself to things as much as I could, to learn the skills required to round it out. But it isn't just about the technology. Technology is always at the core, but it's about all of the rest of the skills as well. Achieve that. There's something about this. Yeah. So it's a great question, and there is just no single recipe. Some of my friends have become world-renowned experts in a very specific, narrow field. World-renowned database experts, as an example. They built a wildly successful career, and others have no such knowledge, but they have great general technology knowledge. They know a little bit about everything. And I think it's honestly a matter of personal preference, whether you want to go deep in a particular area and you're fascinated by that area, and that is still your life purpose. You still need all of these other skills that I talked about if you do that to really maximize the level of success. But others, I would put myself in that camp. I didn't have a huge passion for any one technology area. I liked the whole thing. I wanted to be dangerous in the level of knowledge that I had. I read it, but there was at least a healthy curiosity there that I could ask good questions. And there is no one formula that works for each person. I think you have to look inside of yourself and figure out, what do I really want to do, and how do I fit myself with all of those skills that I actually need to maximize the level of success. And that takes a long time. You make lots of mistakes. It's one of the things I really did not to talk about successes. Every success I talk about a embarrassing failure I had as well. The things that I tried to remember that I thought would resonate with fairly standard learnings in many ways, but they're all communicated. Engineers and let's face it, we're not, many of us, I don't know how many of you, I certainly wasn't on the drama team. I didn't have great experience in front of a lot of people, and learnings that some people that they favor for the arts may have had a natural head start. Communicate, going and they're all skills. Well, I mean, networking opportunities within engineering. It's a hard direct answer. I mean, I can't say that there's these great networking events out there that are general. I would say that when you do have the opportunity, first company that you join, it is critical to get to know people. It is critical to put yourself out there, not to sit in your in your cubicle and do your work. Have no, you've gotta, in the right way, be confidence in yourself to talk to leaders, to talk to peers, and as you move into leadership, it's very important to make that easy for your employees. One of the things I always used to do as a leader was as soon as a new group of employees started, I would have a round that bring in and that wasn't just for that one time get to know each other. It's so that every time you pass by each other in the hallway, you have something, you have a knowledge of that person, you know each other's names. To make it easier to have that connection. So when you run into something, share, and tell leaders and others. This fans out over a period of time. Whenever people are considered for promotions, it's always, well, who is that guy? What's he done? And so much easier if the 7 leaders that are in the room discussing somebody's promotion says, I know that guy. He's done this, he's done that, he's done this. I know my team really likes working with a lot of people on my team. So better you can get out there, make yourself well known, the easier it's going to be to Thank you very much. Appreciate it. Wow, very nice. Look at that. Thank you very much. I will put them proudly in my office.
Also, we would like to award you one gift of your choice. Starbucks Elite.
Here, I'll close my eyes and I'll pick. How's that?
Okay.
Oh, can't see. Oh, I can't do it like that.
All right. Where were you?
All right.
Oh.
I know that one.
Yeah.
Yeah. Thank you very much. Appreciate it. Thank you. Thank you very much. Thanks. Nice meeting you.
Right. So now, we now have
And I hope you guys. All right.
HDMI. Okay, well, good evening, everyone. Thanks for coming out. My name is Hugh Chusser. I teach in the space engineering program here at York. I didn't make up a all about me page, but I'll maybe hit the highlights. So as Professor Rivsey said, mechanical engineers can do anything. So I was an undergrad mechanical engineering at U of T, graduated in '85 and then did a master's in '87. Then I wanted to do my PhD, but I thought I liked money and I wanted to see what the job market was like. So I went out and I worked. And my advice to you is if you are considering a PhD, do it when you can, because I got married, we had kids, so I never got the chance to go back. I went to a company just down the street here, Astra Aerospace, it was called at the time. They've since moved on to telecommunications, so they make phones and that sort of thing. I kind of saw the writing on the wall, so I was there for 3 or 4 years. I moved from there to ComDev, which is now Honeywell Aerospace in Cambridge. I was there for about 6 years, maybe 8 years. And then we decided to move the family. We went out to Winnipeg. So I worked at Magellan. It was Bristol Aerospace at the time. They were owned by Rolls-Royce. So my business card looks really impressive. Then I came back to Toronto. I worked at UTIUS at the Space Flight Lab, where we did the MOST program. I left there. I went to MDA, and then MDA was about to go on strike. Engineers were not being well paid, so they went on strike. Just before the strike, I moved here to take up a position. That was in 2006. So I've been here since then. I guess that's my longest stop. And I think I intersected Peter, the previous speaker, by a couple of years undergrad. So I was at U of T about the same time he did. Okay, so what I want to talk about is why space engineering, and then I'll just kind of go through a program overview. I'm not a research, so I don't have a PhD, so I'm not a research faculty member. I'm a teaching stream, so I teach a lot of the courses in the program. I've experience with those. That's why I'm not talking about my research interests. So why space engineering? I'm just going to blatantly copy the York write the future, or not write, but write, W-R-I-T-E, the future, okay? And that's because of the large number of opportunities currently in space engineering in Canada. I'm just going to talk about a few of these. So writing the future could mean going to GHGSat in Montreal, where they're designing and operating a constellation of greenhouse gas emission detection equipment that's in orbit. There are a huge number of our previous students working at MDA in Brampton. I do a bit of consulting there every so often, and I was sitting at my desk there, and about 10, 12 students came up to me and said, "Hey, sir, I had you for this course or that course." So there's a huge number of students there. They're working on something called GERS. That stands for Gateway External Robotic System. So they're designing the robots that will be on this lunar orbiting platform. Internet in space. So there's a student that we graduated from our program who is working at Kepler. So they're designing a set of communications devices also in orbit to provide network services. Also Telesat, there's Lightspeed. There's a couple of students there at Telesat in Ottawa working on that. That's a low Earth orbit. So the geosynchronous satellites that are doing communications, that's kind of going the way of the dinosaur. It's now low Earth orbit where we can offer phone and internet communications at a light speed, like they're saying. There's a couple of students are working at a new company called Canadensis. That's out in Caledon. They're designing a lunar rover for the Canadian Space Agency. That's associated with the GERS program, the Gateway program. And I don't think we have any students yet at Earth Daily. Has anyone heard of a company called EarthCast? We were they proposing to build a constellation of synthetic aperture radar satellites. And that they ran out of money. So they reformed, and somebody else will be operating their satellites for them, but they will do all of the analytics. So the data science associated with taking all of this data, the petabytes of data that are coming down all the time, and processing them, turning them into data products for different companies that need to know about geospatial data. A couple of other, this Earth Fence, that's a company, Thoth, they're in Deep River, which is up near the Algonquin Radio Observatory. So they've constructed a radar. First of all, they had to refurbish a 1960s huge dish, 42 meter in diameter, and now they're offering services of radar tracking. And then we also have a student working at Honeywell Aerospace in Cambridge, working on the KeySat program. That's a quantum encryption. And so what they're trying to demonstrate is basically unhackable computer networking using quantum computers. So it's they're billing that as sort of the future. So I would say the program, even though it's only one in existence in Canada, contrary to what you might have been told, that the job prospects are not that good, they're actually quite good at the moment. Every industry goes up and down, but right now there's a lot of work out there, and our graduates are getting it. Okay, Gateway, I can play a little bit about this. So this is the CSA contribution. Yeah, this is all really great stuff. But basically what we're supplying. You saw those two robots? That's what we're supplying, a very long robot, a shorter robot, and some end effectors and some of the tooling that goes on to that. And then as part of that, we get some of the, I guess, research or experimentation time on the moon. And that's where the lunar rover comes in. So graduate student working on both of those. Then there's the Lightspeed. That's another huge program. So that Telesat. So everyone's heard of Space Link. And what's the OneWeb? And Amazon is actually just announced they're doing a satellite constellation. Well, Telesat is also doing that as well.
As our world grows, so too do the demands for superior connectivity from today's advanced communications technologies. But with these demands come entirely new challenges, from keeping up with the ever-increasing speed and consumption of data to meeting and exceeding new levels of security and resiliency. So what does it take to tackle these complex challenges, to deliver local solutions at a global scale, to take next-generation technologies further, to connect the unconnected? That is our mission for growth. And our low Earth orbit satellite network, Lightspeed, is set to revolutionize global communications, close the digital divide, set new levels of performance by accelerating 4G and 5G reach, and extend the potential of our customers' technologies. By powering the next generation of reliable, high-speed in-flight connectivity for pilots, passengers, and crew, with scalable, concentrated capacity around large airport hubs and along high traffic routes. By delivering.
Anyway, I thought I would show you that. So there's all kinds of opportunities out there, and students in our program are getting jobs in these areas. Okay, so about the program. So if you break down a typical space system, it's operating in space. It has a space structure. It's driven by electronic circuits, the software running on it. And I guess the only other thing that's isn't in the automation system that Peter just talked about is RF communications. So commands and commands are sent to the system, and telemetry is received, or data is received back via radio, typically radio links, although with KeySat, perhaps laser communications and quantum. So basically, these are mechatronic systems, okay? So that they're, but with the special idea that they're operating in space. So basically, our curriculum is built around this idea that we have these different areas, and that we have to introduce the students in our undergraduate program to this kind of broad range, so that as a mechanical engineer, I was astounded working at some of these aerospace companies about the other disciplines and the other things that they know. Whereas in the space engineering curriculum, we actually introduce you to some of these particular areas. I'm going to talk a little bit about vibration and TVAC testing. We also do in the program some GPS satellite tracking. So you'll write some software here. In the vibration area, you'll do some structural analysis. In the TVAC testing, also thermal or heat transfer analysis. Some of the tools, we're trying to mimic or use the same kinds of tools that you would see working in industry. So we're using Siemens NX for our CAD system. For structural analysis, we have NX Nastran. So Nastran is a typical aerospace, or I would say space finite element tool. And then for finite difference or thermal analysis, we use something called space thermal. So that's the mechanical side. We also do Altium Designer. So we teach the students about circuit layouts and analysis using something called Altium Spice. And then for some of those cool orbit trajectory analyses, we have something called Systems Toolkit. Okay, and then languages, we are kind of changing those around, but at the moment, Python, LabVIEW, we also introduce the students to that, and other languages as well. Okay, so I'll just talk a little bit about this vibration experiment. So we have, we get you doing a finite element model of this circuit board here. Okay, so you're predicting the resonant frequencies of this structure. We then take it into the vibration lab where we conduct a vibration test of the board. So here so we set it up. Here you'll see this is the control system operating here. That's the control accelerometer. And here we've got a monitoring accelerometer mounted on the board. Zoom in here. Okay, so we have a monitoring accelerometer mounted on the board. That's what this channel is showing. So we're looking at some resonances. We go back and we compare these two, maybe make adjustments to the model, repredict, and try to come to what we were measuring. And then once that's completed, once we're happy with the correlation, then we can take a look at the stresses that would result and then predict whether or not the system will fail during launch or not. Okay, then to sort of emphasize the mechatronics aspect of this, so this is that was a third-year experiment, and then in fourth year we take this same board that I talked about before. It has a number of accelerometers mounted on it, and what we do is we drive this board to measure from the different locations the accelerations. Okay, so we're looking at the mechanical aspects of the component, and then we look at the electrical. Okay, so we're combining and then writing software to acquire the measurements. Okay, and then the other thing I'm sort of working on, we have a TVAC chamber in the basement of Petrie. Okay, so we've planned out an experiment, but then of course COVID kind of reared its head. So headway's been pretty slow on this, but the idea is to, so the vibration, of course, simulates the launch environment. The TVAC chamber is intended to simulate the on-orbit environment for the spacecraft. So this chamber here is evacuated to about 10 to the minus 4, 10 to the minus 5, 4 millibar. And then the inside, we have an article that we're testing. So for example, a CubeSat, we illuminate it using a number of different infrared lamps, which is simulating the inputs from the sun and the reflected solar from the earth. And then we measure the temperatures. We also have to measure how much heat we're putting in. So we're measuring the inputs and then the temperature outputs. Now, for something this small, if we put a large number of temperature sensors on it, we're going to affect the results slightly. So what I'm kind of working on, maybe this is too big. This is kind of fuzzy. Oh, now it's even more fuzzier. But the idea here is we're going to use non-contact, at least for the external components inside the TVAC chamber, using some low-cost bolometer-based cameras. So that's kind of the, I wouldn't say it's research, but it's kind of development work that I think, curriculum development. Okay, any questions on that? For research, I don't do research. I'm actually a teaching stream professor, but I do work like this. So I work with, I guess, existing things. I don't do like cutting edge, like software development or anything like that. I'm working with current hardware and then looking at what hardware we need in order to improve the courses that you're taking. Any other questions? Yeah. Yes, well, so we started putting together all of the components here. Okay, so we've got, the sort of the frame put together. The next thing is trying to clean up this bottom plate here. So that's kind of the next step. But we have all the components in place. It's a question of getting it together, testing it out, making sure that it's not a 1-week test. That's the other thing is when you run a TVAC test, it can be a 24/7. Well, it is a 24/7 activity because once you close the door, you don't want to. Oh, it's time to go home now. Let's let it back up to air, and it's not. It doesn't work that way. So yeah, that's one of the challenges is to try and keep it to a relatively short time frame. Unless you want to stay 24/7 until we're finished. Anyway, yeah, so yeah. This is a 3rd-year heat transfer course. So we do, so the other mechanical people, they would do convection and conduction and radiation. Whereas in this course, we just focus on basically radiation and conduction. Okay, so let's see. Last semester, I was teaching space hardware. So that's that 4th-year course where we were looking at the digital signals coming from the accelerometer. I was teaching 4360, which is the space payloads course, where we're learning about different space payloads, including some of the ones that I talked about in some of the projects that are. And then 3360, which is the heat transfer. This semester, I'm teaching a 2nd-year course in computers. So we're programming. So we're learning about Python. I also like to get the students working with assembly level coding as well. So we're actually generating machine code. So you can see that transfer from machine code right into the bytes, the bits that go into the computer. Then we talk about Python, which is a higher level code. So that lets me talk about levels of abstraction, other computer concepts. And then the second half of space hardware is the other course I'm teaching. So this semester in space hardware, we're doing radio RF circuit experiments. Then we're doing some software development. We're training the ARO dish to track or keep, we're writing code to track GPS satellites through the sky and receiving the data. Once we then go to ARO itself and we test out the code and see. Any other questions? I think Peter was about right, 5 or 6 years at one location. Otherwise, if it's shorter than that, you don't really get to know the people and the places that are.